Good day, this is Professor Will, CBMD PhD, and today is Thursday, October 21st, 2021. It is 4:25 and 36 seconds, a.m. Eastern Standard Time. Today's research, dark energy. So let's hop to it here. Hunting dark energy with gravity resonance. Spectroscopy. Date June 29, 2021. Source Springer. Researchers demonstrate a robust experimental technique for studying one particular theory for dark energy, named gravity resonance spectroscopy. Their approach can bring researchers a step closer to understanding one of the greatest mysteries in cosmology. Dark energy is widely believed to be the driving force behind the universe's accelerating expansion, and several theories have now been proposed to explain its elusive nature. However, these theories predict that its influence on quantum scales must be vanishingly small, and experiments so far have not been accurate enough to either verify or discredit them. The previous phenomena named scalar semitron fields have been proposed as a potential candidate for dark energy. If they exist, these fields will be far weaker than gravity, currently the weakest fundamental force known to physics. Therefore, by searching for extremely subtle anomalies in the behaviors of quantum particles trapped in gravitational fields, researchers can prove the existence of these fields experimentally. Within a gravitational field, ultra-cold neutrons can assume several discrete quantum states, which vary depending on the strength of the field. And through GRS, these neutrons are made to transition to higher energy quantum states by the finely tuned mechanical oscillations of a near-perfect mirror. Any shifts from the expected values for the energy differences between these states can then indicate the influence of dark energy. The research study demonstrated a GRS experiment named Q-bounce, which they based around a technique named Ramsey spectroscopy. This involved causing neutrons in an ultra-cold beam to transition to higher energy quantum states before scattering away in unwanted states and picking up the remaining neutrons in a detector. And through precise measurements of the energy differences between particular states, the researchers can place far more stringent bounds on the parameters of scalar semitron fields, and this technique now paves the way for even more precise searches for dark energy in future research. Good day, this is Professor Will, CBMD PhD, on space science, astronomy, and advanced physics. This video was created for educational purposes only. Hope you enjoyed listening. Until next time, have a great day.